Let us now study the combined mechanism in detail. For simplicity, let us consider the structure under vertical loads only. As we have learned before, in this mechanism, the left column and the immediate beam, that is segment A, B, C, stays rigid and it undergoes rotation about A. Similarly, D and E, they are also hinged. The only joint which does not undergo hinge formation is B. ED undergoes rotation about E. Finally, the new positions of C and E, that is C dash and D dash, they are defined by the conditions of inextensibility of CD. In all these displacements, triangle ABC remains rigid. So last time we had defined angle of BC with horizontal as gamma, which we are showing now. Besides this, we also defined the angle made by CA with horizontal as beta. Both beta and gamma are shown here. So as we had informed earlier, our assumption is that the virtual rotations undergone about A and E, they are very small as compared to the angles beta and gamma. Let us now execute the process in detail so that we can find out the relationship between the angles of rotation undergone by various members. We extend AC and also extend ED such that they meet at I, which is the instantaneous center of rotation. Just note that this is different from the instantaneous center of rotation considered in the beam column mechanism, where we were extending BC. Now we are extending AC instead of BC. Let now the structure be at the verge of collapse and we impart a very small virtual rotation phi about I, This gives rise to a rotation theta about A and a rotation alpha about E, as shown here. While segment ABC undergoes rotation theta and ED undergoes rotation alpha, the rotation undergone by segment CD is same as phi because it's part of triangle ICD, which remains rigid. So C moves to C dash such that it's normal to AC, D moves to D dash such that it's normal to ED. Note that triangle DCI stays a rigid triangle in this process. So we can now draw the profile of the deformed structure after the formation of the mechanism like this. Now CC dash from trigonometry can be written as equal to AC into theta, and this is also equal to IC into phi. Hence we get a relationship between theta and phi as theta equal to IC by AC phi. Next we can similarly write DD dash equal to ED into alpha, and this is also equal to ID into phi. This gives us the relationship between alpha and phi, alpha equal to ID by ED phi. So we have expressed both the variables theta and alpha in terms of phi. All we have to do is find out the lengths of the sides IC, AC, ID and ED, and we'll be able to get the exact relationship between the various angles. So here PU is the load acting at C. So basically PU moves down vertically from C to C double dash, and we have to find out how much is the vertical displacement. So we are zooming into this region and drawing the triangle separately here. So we draw the triangle C double dash C, where the angle at the vertex C double dash is 90 degrees. So C dash is AC into theta, and now the vertical displacement undergone by the load PU is C double dash. Now we can express this also in terms of theta and hence in terms of phi once we use the trigonometry in triangle C dash C double dash. So this angle at vertex C is equal to beta, which is the angle which BC makes with horizontal, because the displacement CC dash is normal to BC. So this angle with the vertical as shown here will be beta. Hence, the value of the vertical displacement under the load, that is C double dash, is equal to CC dash cos beta, that is AC theta into cos beta. Note that AC cos beta is basically the horizontal projection of AC, and this is equal to 5 meters. Hence, the vertical displacement is 5 times theta, and this is same as in the case of the beam column mechanism. Now theta can be expressed in terms of phi also. Now we are in position to write the equation for the virtual work. So we equate the external virtual work with the internal virtual work. So at A, the rotation undergone is theta. So the work done is MP theta. At joint C, the rotation undergone is theta plus phi. So the work done is MP into theta plus phi. At D, it is similarly phi plus alpha, and at E, it's alpha. So we have set up the equation equating the internal and the external virtual works. So we can solve this equation and find out the value of PU. So we can compare the PU obtained from this mechanism with that from the beam column mechanism, and then we can find which one is the lower. For the lower of the two mechanisms, we can carry out the equilibrium and the yield checks to ascertain that the chosen mechanism is the actual collapse mechanism. So we have used the instantaneous center of rotation approach for finding out the relationship between various angles of rotation. Now there is one more alternate approach which does not need rotation about the instantaneous center of rotation. So this is called as cut and join approach, and we'll evaluate the combined mechanism in light of this method also. So note here the angles beta and gamma we are marking here. These will be very crucial in the trigonometric formulations that we will be using in this particular approach. So please pay careful attention. let us temporarily introduce a cut in the structure at joint D. But we assume that we are holding the two parts temporarily. Next, we apply a very small virtual rotation of the part ABCD about A. But we do it such a way that CD remains parallel to itself. So C moves to C dash, D moves to D dash, but we deliberately keep CD and C dash D dash parallel to each other. So assumption is that we are keeping all the parts temporarily on hold. So both being the opposite edges of a parallelogram, CC dash is equal to DD dash. Now with ES center and ED as radius, we draw an arc, and let's call this arc as A1. Since the radius of the arc is very large, so the arc appears like a straight line. We have to locate the actual and the final position of D. So for that purpose, we draw another arc with C dash as center, C dash D dash as radius. We draw arc A2. Now the two arcs A1 and A2, they will intersect each other, and that will give us the final location of D. So this process basically satisfies the condition that all the members are inextensible. So D double dash is the final position of D. So now we can draw the deformed profile of the display structure. Let us now zoom this particular triangle D, D dash, D double dash to find out the relationship between the various displacements and the rotations. We assume that ED undergoes a rotation alpha about E and the segment ABC undergoes the rotation theta about A. CD, it undergoes rotation phi, but note that the rotation phi is opposite to theta and alpha. So the displacement DD dash is equal to ED alpha, and now we draw the segment DD dash. So DD dash will be normal to line AC, and AC is making an angle beta with the horizontal. Hence, the angle made by the vertex D is basically 90 minus beta. Now we see D dash, D double dash. Now this displacement, this is part of arc A2, so this must be normal to C dash, D dash. So C dash, D dash, it is inclined at an angle of gamma, hence the angle made by the vertex D double dash must be 90 minus gamma. Now the third angle must be beta plus gamma by the fact that the sum of the internal angles of a triangle is 180 degrees. We can also write CC dash as AC theta, and we can write D dash, D double dash as CD into phi. Now we simply apply sine rule to triangle D, D dash, D double dash. So applying this rule, we can write D, D double dash divided by sine of beta plus gamma equal to DD dash divided by sine of 90 minus gamma, and must be equal to D dash, D double dash divided by sine of 90 minus beta. We can then substitute the values of these displacements such as D, D double dash, D, D dash and D dash, D double dash in terms of the angles alpha, theta and phi, and we already have the relationship between these angles. So we can solve the equation of virtual work, and based on that we can find out the ultimate load for this particular mechanism. So this is the alternate method. Now we simply apply sine rule to triangle D, D dash, D double dash. So applying this rule, we can write dd dash divided by sine of the opposite angle, that is d double dash divided by sine of beta plus gamma equal to dd dash divided by sine of 90 minus gamma, and must be equal to d dash d double dash divided by sine of 90 minus beta. We can then substitute the values of these displacements such as d double dash, d dash and d dash d double dash in terms of the angles alpha, theta and phi, and we already have the relationship between these angles. So then we can solve this equation and we can get the solution. So we can solve the equation of virtual work, and based on that we can find out the ultimate load for this particular mechanism. So this is the alternate method. It does not involve the instantaneous center of rotation, but it basically involves cut and join approach, which we have learned. So it is up to you to follow either the cut and join approach or the instantaneous center of rotation approach. We have taught you both. It does not involve the instantaneous center of rotation, but it basically involves cut and join approach, which we have learned. So it is up to you to follow either the cut and join approach or the instantaneous center of rotation approach. We have taught you both. So far we have assumed symmetrical frames. Now we give you an exercise involving unsymmetrical frames. So it's your homework that if we are solving unsymmetrical inclined portal frames under either vertical load or two horizontal loads at the two column tops, then you use the knowledge learned and try to find out which mechanisms are possible. Possibly some of the mechanisms can be eliminated in each case. Thank you very much. We recommend a home practice of all the problems related to inclined portal frames we have done today.